Somewhere beyond the reach of rockets and reason, there may exist a path through the universe that defies everything we know about space and time. A bridge, not across the cosmos, but through it. Theoretically, such a passage could connect two distant points in an instant. Two galaxies, two moments in time. A journey that, in one step, bypasses light years. A door in the universe. Physicists call it a wormhole, a speculative tunnel carved into the very fabric of reality. But these structures are not just conduits through space. The true mystery lies in their relationship with time. Could wormholes offer us a way not only to travel faster than light, but also to loop backward in time? Could they let us revisit the past or jump into the far future? And if so, what would that mean for our understanding of causality, free will, and the nature of existence itself? This is not just science fiction. It is science, on the very edge of what we know. Welcome to the paradox of wormholes. To understand wormholes, we must first understand space-time. Einstein taught us that space and time are not separate entities. They are woven together into a single, malleable fabric, space-time. This fabric can bend, stretch, and twist under the influence of mass and energy. Now imagine that this fabric, vast and incomprehensible as it is, could be folded in on itself. If two distant regions of space-time were brought close together by such a fold, it might be possible to connect them with a tunnel, a shortcut from one place or time to another. That's a wormhole. The concept first appeared in a 1935 paper by Einstein and Rosen, who theorized a kind of bridge, now called the Einstein-Rosen bridge, linking two black holes. But their solution described a structure that would collapse instantly if anything tried to pass through. Still, the math opened a door, and ever since, physicists have been asking, could there be a way to stabilize such a bridge? Could a wormhole actually exist? And could we travel through it? Here's the challenge. Gravity doesn't like wormholes. If you were to somehow create a tunnel in space-time, the immense gravitational forces would cause it to pinch shut immediately. The very structure would collapse into itself, leaving no time to step through. To keep it open, you would need something incredibly unusual: exotic matter. Unlike normal matter, exotic matter would exert negative pressure, a kind of repulsive force that pushes outward rather than pulling inward. This idea may sound like fantasy, but quantum physics offers a clue. The Casimir effect, a phenomenon observed in a vacuum between two close plates, creates a measurable force due to quantum fluctuations. This is real-world evidence of negative energy density. Could we harness such forces to keep a wormhole open? Could exotic matter be created or extracted? If so, we might one day engineer a wormhole that remains stable long enough for passage. But even if we could keep the structure open, another, stranger possibility arises: time travel. Here's where physics takes a mind-bending turn. Imagine a wormhole with two ends, or mouths. Now imagine taking one mouth on a journey through space at near-light speed, while the other stays stationary. According to Einstein's theory of relativity, time will pass more slowly for the moving mouth than for the stationary one. When the moving mouth returns, you'll have two mouths, connected by the same tunnel, existing at two different points in time. This means you could enter one mouth in the present and emerge from the other in the past. This would not be theoretical time travel in the abstract. It would be physically stepping through a portal and emerging in a different era. One moment you're in the year 2100. The next, you step out into 1984. It seems fantastical, yet the mathematics of general relativity allow for this exact scenario. The laws of physics don't outright forbid it, but nature may. If time travel through wormholes is possible, then we face one of the most profound threats to logic, the paradox. Suppose you traveled through a wormhole and prevented your grandparents from meeting. That act would erase your own birth. Yet if you were never born, how could you go back and stop them? This is the grandfather paradox, a loop that breaks the chain of causality. And it's just the beginning. Physicists have proposed various ways to resolve such contradictions. One is the Novikov self-consistency principle, which states that events in time travel must be internally consistent. You can visit the past, but only in a way that fulfills, rather than contradicts, history. Another possible solution involves the many worlds interpretation of quantum mechanics. In this view, each time a decision or paradox emerges, reality splits, creating a new timeline where both outcomes exist simultaneously. In this framework, time travel doesn't change the past. It merely branches into another universe. But this, too, leads to troubling implications. Are there infinite versions of ourselves? Infinite pasts? Infinite futures? And if so, which one is real? Theoretically, wormholes might exist in nature. But have we found one? So far, no wormhole has been confirmed by observation. But scientists are looking. Some believe that black holes, those mysterious gravitational sinks that warp time, could be connected to distant points in space, forming natural wormholes. But these would likely be non-traversable. Anything entering would be crushed at the singularity. Others suggest that quantum foam, the turbulent substructure of space-time at the Planck scale, might contain microscopic wormholes flickering in and out of existence. Too small for us to detect or use, but perhaps someday we'll learn how to stabilize and enlarge them. And then there's the radical idea that entangled particles, a cornerstone of quantum mechanics, are actually connected by wormholes. This idea, known as ER equals EPR, proposes that wormholes and quantum entanglement are two sides of the same coin. It suggests that the universe itself may be knitted together by invisible threads of connection, tiny wormholes forming the fabric of reality. Even if wormholes could be built or found, what would happen if we used one? Would causality break down? Could we accidentally destroy history by altering the past? Or worse, create temporal feedback loops where energy and matter cycle endlessly, building to catastrophic instability? And what about information? Could data be sent backward in time? Could a message be delivered to warn of disasters or manipulate outcomes? If wormholes allow information or people to move freely through time, then power becomes infinite. And power without consequence is dangerous. This is the heart of the wormhole paradox. A technology that unlocks the secrets of the universe may also unravel it. For now, wormholes remain speculative, brilliant concepts waiting for evidence. But the tools we use to search are improving. We're building gravitational wave detectors capable of sensing cosmic disturbances that could signal wormholes. We're refining our understanding of quantum mechanics and space-time at the most fundamental level. And through advances in AI, computation, and cosmology, we're testing the boundaries of the possible. Perhaps the wormhole is not a bridge for travel, but a mirror, a symbol of the lengths we'll go to answer the most profound questions. What is time? Where are we going? And could we ever go back? The idea of wormholes forces us to rethink the limits of the universe. It forces us to ask, is time a straight line? Or is it a circle? A loop? A web of possibilities yet unrealized? If we could open such a door, would we walk through it? And if we did, would we find our past or lose ourselves in it? Perhaps the wormhole is not a path to the stars, but a reflection of the deepest human longing to go back, to fix what was broken, to relive what was lost. Or perhaps it is a signpost, pointing forward, urging us not to retreat into the past, but to press into a future we do not yet understand. Wormholes challenge our understanding of physics, logic, and even existence. They remain the ultimate paradox, a structure that could take us anywhere, at any time, and yet may be forever beyond our reach. Still, the questions they raise are worth exploring, because even if we never walk through one, the act of imagining them may open other doors.